So in this video, I'm going to show you how you can derive a template. And the way this works is that if you're given a sequence, you can test it against this template, which is just a list of 4 formulas. And using these, you'll get a general formula, and then you would test that against uh, your given first few terms to see if it matches. So here's how you can derive this. So this is for arithmetic plus a geometric sequence. So if I have an arithmetic sequence that goes mn plus b, and a geometric that goes ar to the n plus k, and I add these two, I'll say an plus bn is c sub n. So then c sub n is going to be ar to the n plus mn plus, and then now we're going to add b and k, so we can just say that b plus k is s, because we're just adding two variables, so we're going to get another variable. And now let's say the terms of my c sub n are c0, c1, c2, c3, and so on. Now I'm going to use systems of equations, and the reason I'm going to use that is my goal is to solve A, R, M, and S all in terms of these terms, which are just constants. So here's how I'll do that. So C0 is going to be A plus S, and I'm just going to write out all of the systems of equations for what I'm given. So now we have these 4 equations, and this should be enough to solve for all of these variables in terms of constants. And the best strategy to do so, to eliminate as many variables as possible, is to use second common differences. And just to refresh on what that means, let's say we have a sequence n squared, which is 0, 1, 4, 9, 16. So the second common difference, if we take the differences of each term, we get this. And then the second common difference is just the differences of these. And the way we can also derive the second common difference, and this can be proven, is by just, if we start at 0, let's say, we would go to the term which is 2 terms out of it, which is 4. So we have here, and then we do 4 minus the term before it, 2 times the term before it. So that'd be 4 minus 2 times 1 plus 0. And this is actually how the second common difference works, but yeah, this can be proven as well. And now we can use this to our advantage. So I'm just going to do that for the equations from C0 to C2. So this will look like, and now 2 times C1 is going to be, I'm going to subtract the 2, and now I add C0, which is A plus S equals C0. So I'll be left with, okay, so now I have one equation, and this equation is only in terms of A and R, which is really good. So now we can repeat this to get another equation which is only in terms of A and R by just doing the same thing, but instead of doing it from C0 to C2, we now do it from C1 to C3. So let's do that. So this is just rewriting C3, and then 2 times C2. Now I subtract the 2, and I have, And now I'll add C1, AR plus M plus S equals C1. M and S cancel. And now we have two equations now. So, and this one is also only in terms of A and R, which is really good. So we have this equation, and we have this equation. And if we look at these two equations, we see there's something very similar about them. Because if you were to multiply this one right here by R, you get AR cubed minus 2AR squared plus AR, and then R times this. But then AR cubed minus 2AR squared plus AR is exactly what we have here. That means we can multiply this by R, and then if we do that, we're going to get R times C2 minus 2C1 plus C0. And then we already know that this value right here is just C3 minus 2C2 plus C1. And now we have an equation which is only in terms of R and constants, which is perfect. Because now that we have this, we can always solve for R, and then if we solve for R, we can find A, because this one only has two variables. If we find R and A, then we can go back to this equation to find M, and so on. We can also find S from the first equation as well. So this works really well, and just to summarize the results that we got, we can go to this table here, and we can see this first thing is exactly what we got. So now that we have these equations, let's see an example of this in action. So let's say I'm given 3 times 2 to the n plus n. So the given would be the terms that would come from this. This would be our answer eventually, but we're trying to derive this. So if n is 0, then so I'm just writing out the terms. 0, 1, 2, 3 would be 27. Yeah. So now that we have the first few terms, let's say that we were only given this, and now we're trying to figure out what the general formula is for this. So to do that, we can refer to our template. And the first equation for our template is this one. And I'm just going to rewrite that. And now we can easily find R. So if we look at this, this is just the second common difference from the first term to the third term. So that would be, so we see that this right here is 3. So we have 3 times R. And then if we do the same thing again, then we're going to get plus 7 plus 13, so plus 6. So this is 6, so that means that R is 2. And now from a previous equation, we can now use this R to find A. So AR squared minus 2AR plus A equals C2 minus 2C1 plus C0. And R is 2, so we have 4A minus 4A plus A equals, And we already know that this was 3. So A is 3. And with A and R, we can now refer to this equation. M plus AR minus A is C1 minus C0. So that would be, so R is 2, A is 3. So this is 6 minus 3. C1 minus C0 was 4. 7 minus 3. So M plus 3 is 4, so M is 1. And now that we have these 3 variables, we can also find the last one, which is S. A plus S equals C0. In this case, our first term was 3, so that's C0. So C0 is 3. And A was 3. So that means that S is 0. So now we have our 4 variables and the values for them. So now we can just plug them into our equation, which is AR to the N plus MN plus S. So this is going to be 3 times 2 to the N plus N, and that's it, yeah. So if we were to test this, it would actually match what we have with these first few terms here, and you can test that. So this template is really useful when we don't really know if there's a pattern between the terms, because often we don't know if there's a pattern between the terms, but we can test this to figure out if this is a result of a geometric plus an arithmetic sequence, in which it would be really easy to find this general formula. So this concludes this episode on uh, arithmetic plus geometric, and uh, yeah, hopefully you found it helpful. Thank you for watching.